So, welcome back student to the next class of complex analysis, where we are dealing with something called Laurent series. This is a series we described last class, that where the function is analytic in some region, annular region, defined by this. So, the restriction is something like this annular region, the function is analytic, and for this region I can expand the function like this. And this part we mentioned, this part is called the principal part and this part is called the analytic part. So, last day also, in the last class also, we put some kind of example in front of you, which gives you the idea how the singularity is calculated or how the singularity is coming in the light of this expansion, Laurent series expansion. So, today we will give another example where we find that there are simple kind of singularity, there is no singularity, removable singularity. So, all the singularity are isolated here. You should note that at z equal to z point only we have some singularity, like the function f z. This function has isolated singularity at z equal to 1 point. Apart from that, this function is analytic. So, this z equal to 1 is called the isolated singularity, and this is having a simple pole. But if I multiply here say 3, then this function has a pole of order 3 and so on. But there are few function also which has some essential singularity. So, for example, the function f z is something like z plus 3 z minus 3 sine of 1 by z minus 2, if this is the function, if this function look like this way. So, how to deal with that? So, then I mean there are two ways. So, I can write this z minus 3 as z minus 2 plus minus 1 and then sine of 1 by z minus 2, and then if I multiply I will have z minus 2 sine 1 by z minus 2. This is the first part, and second part is minus sine of 1 by z minus 2. Now, if I expand this function, if I start expanding this function, so the first part will be expanded in this way, z minus 2 multiplied by, the first term is 1, second term is minus, z minus 2 cube divided by factorial 3, then plus z minus of 2 5 factorial 5 and this. But this function on the other hand is expanded, oh sorry, I am making one mistake, it is 1 by z minus 2. So, it will be 1 divided by factorial 3 z minus 2 cube plus 1 by factorial 5 z minus 2 5 and so on. Next part is also represented like this, 1 minus 1 by factorial 3 z minus 2 cube plus 1 by factorial 5 z minus 2 5 and so on. So, 2 part I separate out, and if I write it here finally, then this function is represented like first part is z minus 2, then the next part is 1 divided by factorial 3 z minus 2 square, then plus 1 by factorial 5 z minus 2 4 to the power 4 and so on. Along with that we have this part also. So, minus 1 plus 1 by factorial 3 z minus 2 cube and so on. So, this is my total function, total expansion. So, in total expansion we find that this is one, you find that this entire portion, this portion except these 2 point minus 1 here and z minus 2 are principal part. So, this is your principal part, this is your analytic part. So, we have only 2 analytic part here and infinite number of principal parts. So, that means at z equal to 2 point this function has an essential singularity. So, the conclusion is at z equal to 2 point, at z equal to 2 the function has essential singularity. Essential because you can't remove this singularity at that particular point, whatever the function we have, because we have limited number of analytic part, but infinite number of principal parts. So, that means we should have some singularity which is essential is nature. So, now we will go to the next step. Now, I believe you have an idea about the singularity and all these things in the light of Lorard series, but now we need to do some problem regarding the Lorard series. So, how a function is given to you and how you should expand in terms of Lorard series is now the next problem or the next topic that we are going to start. So, let me do with an example, because this is the best way to understand the Lorard series is solving some problems. So, that is why I start with some examples. So, the function here is given to us something like this. If z is say 1 divided by z minus 1 z minus 2, we need to expand this particular function. So, now first you should note that this function has a singularity at z equal to 1 and at z equal to 2, both the singularities are simple poles. So, this function has a pole of order 1, so simple pole, and singularity at the point 1 and 2. Now, the next thing is that we need to expand this function in the regime mod of z less than 2 greater than 1. So, this is the regime where we need to expand this function. As soon as the region is given, because I know that the function where I need to expand this, the region should be where the region is something where the function should be analytic in nature. Here we find that this particular function, whatever the function is given, is analytic in that region, because 1 point and 2 point both are outside. So, let me first define the function, first define the region here, first check where the region should be. So, this is my coordinate system, mod of z is greater than 1 and less than 2. So, let me draw a circle of radius 2, this is a circle of radius 2 suppose, and another circle of radius 1. Okay, so, I have drawn a circle of radius 2 here the radius is 2 and here the radius is 1. Mod of z is less than 2 means all the points less than here, mod of z is greater than 1, that means all the point here. So, the region where we try to expand this function is essentially this annular region. This annular region I am talking about, where the function has to be expanded in terms of Laurent series or in Laurent series. So, this is the region where we need to expand the function, this annular region, the shaded one. Okay. So, here the technique is quite straightforward. So, first in order to do that we can factorize this. So, if I do, it is simply comes out to be z minus 2 minus of 1 by z minus 1. If I do, then I find it is z minus 1 comes here, z minus 2 comes there, z we cancel out, minus 1 plus 2. So, plus 1 will stand here and I have this. So, I can write the same thing in this way. Once I write this, the next important thing that we need to note that this is the limit here. So, once okay. So, when I expand this kind of function, what was the result? The result was z plus z square. So, I can expand this particular function in terms of some series. What is the essential condition behind that? The essential condition was mod of z was less than 1. That was the essential condition we always impose, and based on that I can write this series. So, we will always do the same thing here and try to find out how the series look like. So, here in the first case it suggests mod of z is less than 2, that means mod of z divided by 2 should be less than 1, that is one thing in my hand. And the second thing is 1 is less than mod of z, that means 1 divided by mod of z is less than 1, that is the second thing in my hand. So, when I expand these two condition, I need to take care of these two condition, so that I can expand this particular function in the proper form. So, now if I do that, it will be 1 divided by, take a minus common out. So, minus 2, because I need to make z divided by 2. So, if I do, I will have 1 minus z by 2. 2 multiplied by z by 2, I will have the same thing. So, I just divide in this so that I can have the term z by 2, because my condition suggests z by 2 is less than 1. So, that means I can have the opportunity to expand this in some series. In the next case also it is 1 by z. So, what I will do, that I will take z common and it will be 1 minus 1 by z. Once I take z common out of that, then 1 by z will come, because 1 by z is the required thing, because 1 by z is less than 1 according to the condition. So, now I can expand. So, if I expand, it will be minus of half 1 minus z by 2 whole to the power minus 1, that is the first thing, and the second thing is 1 by z 1 minus 1 by z whole to the power of minus 1. I separate out two part, and now we are we are ready to expand this, because both the condition is in our favor to expand this, because z by 2 is less than 1. So, that means I can expand this, 1 by z is less than 1, I can also expand this in the series. So, if I do, then I will have 1 by 2 1 plus z by 2 plus z square by 2 square plus z cube by 2 cube and so on. That is the first part. Let me erase this. I believe you understand what I am trying to do. Minus 1 by z, this is 1 minus, so this is plus 1 by z plus 1 by z square plus 1 by z cube and so on. Now, I can rearrange these things slightly so that it looks good. So, let me erase this. So, this function eventually comes out to be something like this, plus dot 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 plus 1 by z to the power 4 plus 1 by z to the power of if I take this term, this term, this term and this term, there will be 4 term. So, 4, 3, 2 and 1 up to this. Then I start from here because it is so plus minus half plus z by 2 square plus z square by 2 cube and so on. So, when I expand that, you can readily understand that this portion from here to here, we have this portion is in the expansion is the principal part and this portion in the expansion is the analytic part, and this is basically the desired Laurent series expansion, because the Laurent series expansion should be in this form. The Laurent series expansion should be in this form, a minus k divided by z minus z0 k, k goes from 1 to infinity, and another term a k z minus z0 whole to the power of k, k goes to 0 to infinity. So, there are two parts are associated with the function fz, and this is the function, and this function is evaluated in this annular region with the condition given like this. Based on that condition, if I expand, I find the principal part, that means this part here, and the analytic part, that is this one, where my a0 is nothing but minus of half, and the ak is all the cases the ak is turns up to be 1, and a minus k is all turns to be 1, and ak is comes out to be minus half a0, and first one is 1 by 4, then 1 by 8 and so on. Okay. So, this is a very straightforward example of how to expand a given function in terms of Laurent series when the given region, the region is given to you. Now, we go for another example. So, let me check what other example is we have in our hand. Okay, so the function fz is same. The next example is something similar. The function that is given to same, the only difference is the region. So, the region is given as z minus 1 is less than 1. Okay. The region that is given is this. So, again let us try to find out which region we are talking about. Z minus 1 means I should have here some point here. So, this is my point here, and having a radius 1, if I make a circle of radius 1, not 1, less than 1, I should have a circle here something like this. This is the circle I have. Also note that z minus 1 is greater than 0, that means also here we have a small circle which is my small region, or because it is not at z equal to 1 point, because z equal to 1 point the function is not analytic, you should remember that. So, that means this is the region where I am trying to expand my functions. This is the region where I am try to expand my function all the points in this circle except the center which is at z equal to 1, because it is restricted by this limit. Now again I will try to do the same thing. So the first thing is to write the expression in this factorized form. If I do that, then again I will have in the previous way the old function here. Now one thing here, z minus 1 seems to be less than 1. So 1 by z minus 1 term should be intact here. This quantity is z minus 2. I need to deal with this quantity. So let me do that in this way. Z minus 2 I can write z minus 1 minus 1, right. So if I write this, then I am done actually, because now if I take a minus common here, so it seems to be 1 minus z minus 1 minus z minus 1, because I take a minus common. So it will be 1 minus z with a negative sign. So it will be something like this, minus 1 minus z minus 1. So z minus 1 is less than 1. So no problem with that. I can expand this whatever the function is in my hand, which is minus 1 minus z minus 1 minus this. Now once I have, I can now allow to expand this, because z minus 1 is less than 1. This is the condition I already have, and now I can expand this function, and this function will be something like this. Fz will be minus of 1 plus z minus 1 plus z minus 1 square plus z minus 1 cube dot minus 1 by z minus 1. It will be something like this. So you can see again that I have a principal part here, I have an analytic part here, and if I write in this form, so it will be something like minus of 1 by z minus 1, then minus of 1 minus of z minus 1 minus of z minus 2 square and so on. So this particular form seems to be two part. One is this part, we called it as principal part, only one term in this principal part, and if you remember that this is a simple pole, because my function was z minus 1 z minus 2. So it should have two poles, but if I take the limit at z tends to 1 multiplied by z minus 1 function of z, I will have a quantity which is not equal to 0, or I have a finite limit here. Once I have a finite limit, that means it is having a pole of order 1, and when I expand this in terms of Laurent series, again we are having the same thing, and that is this quantity. So we have one principal term here, and that suggests that it should have one pole in this expression. So now I should conclude the class here, because in the next class we will start again with the Laurent series and try to understand something quite important, which is called the residue. So today we will not have we did not discuss anything about the coefficient that is coming from the Laurent series, which is ak and a minus k, and this coefficient have some significance, because let me give you the idea. If you remember the first part, I write fz in total was represented by this when I expand this in Laurent series minus infinity to k is equal to minus infinity to the infinity. Then we mention ak as 1 by 2 pi I. We did not use this, however, but we will going to use in the next class. What is the significant here? K plus 1. So, now if I put k equal to minus 1, then this equation gives me something quite interesting, and that is this. So, I can eventually have the result of this function. If even if this function have some kind of singularity, I can remove this singularity in that region, and I can have the expression which is nothing but 2 pi I multiplied by a minus 1. So, a minus 1 is nothing but it is a coefficient, and this coefficient is called this residue, and from here the residue theorem emerge, and using that we can calculate many integration and all these things. So, we will in the next class we will start from here. We may go to few other examples of Laurent series expansion, and then directly go to this residue and how to calculate the residue, what is the way to how many different kind of residue you have, and all these things. So, with this note, so let me conclude the class here. So, see you in the next class, where we learn more about this residue and also do some kind of problem related to Laurent series. So, thank you for your attention. See you in the next class.